Now some problems, exam type problems that we have with the ellipse. So the first one we want to do is show the tangent to the ellipse at the point 3,1 has that equation. Well, again, how do we find the tangent to something? Well, we get our derivative. So in this case, because it's in this form, we don't really want to manipulate it too much. We'll use implicit differentiation. So we derive the x squared gives us 2x on 12, y squared would be 2y over the 4, and because we're integrating or differentiating with respect to x, we can have dy dx there, and so we start to cancel, take the x and becomes x on minus x on 6. Then when we go across and cancel, we've got the y on 2 because we've got some cancellation there, and then multiply both sides by 2 on y, and we get the derivative as minus x on 3y. So at the point 3,1, well, we can just substitute x and y in. That gives us our gradient of the tangent there. So minus 1, we've got our point, there's our gradient, as our equation of the tangent. Once we've got to that point, well, it's not too hard to get the equation because we've got our gradient, we've got our equation. So there's the first part. Now we're going to use that in the next part because so if this tangent cuts the directrix in the fourth quadrant at the point T. So there's our directrix, and there's point T, so 3,1 going, it's cutting there. We want to show that, and S is the corresponding focus, so the focus on the same side. We want to show that SP and ST are at right angles. Okay, so we need to get a bit of information first. So firstly, we need to find the focus because we've got no points there, and we need to find our directrix so we can find T. Well, that's not too bad. We've got our equation. We find the eccentricity as b as square root of 1 minus b squared on b squared on a squared, which gives us the square root of 2 on 3. So the focus is a times e, so we multiply that and we get 2 root 2 0. So there's our focus, 2 root 2 0. Our directrix would be a on e, so we'll do that and we get 3 root 2 when we do the multiplication out there. So if you check that out, because that gives you square root of 36 on root 2, and then you can clean it up to get 3 root 2. So to get our other point of P, well, if x is 3 root 2, substitute into the tangent because the tangent actually hits at that point there. So we've got an equation, we've got another line that we can get the y value from. And so we put it in, we solve, and we get y is equal to 4 minus 3 root 2. So there's T. So now we can find the gradients. We'll find the gradient of PS because we've got S, we've got P, we've got T. So we've got P, we've got S, and we've got, so we sub those points in, and for S and T we've got those points, so we sub those in, and we start to manipulate. So we clean it up, we get 3 root 2 minus 4. If I multiply this, the denominators here in the next line, we've got a minus there which will take it out the front. The root 2 multiplies by 3 to give us 3 root 2, and root 2 times 3 root 2 would give us 3 times, sorry, that should be 2 root 2. We've mucked it up there a little bit. We should get the 4 there. So if I should have had 3 minus 2 root 2, so let's clean that up. That should have been 2 root 2. That should have been 2 root 2, which gives me the 4 there. So I've just made a little error. So check that. That should be 3 times 2 root 2 because that was what we had there. So and then so that comes out to the 3 root 2 minus 4, which then they cancel. And then we get the minus 1. Well, we know when two gradients multiply to give us minus 1, we get perpendicular line. So PS then is perpendicular to ST. So there we go. That's that one. So it took a little bit of manipulation, but we were just using all the rules we've learnt to get the eccentricity, focus, directrix, doing some substitution from what we had in part 1, and then using that multiplication of the product and get the products equaling minus 1. In the next one, first part's pretty easy. Like we've got our ellipse there, and we want to find this eccentricity. And as we've done before, we can find our eccentricity. Use the e squared is equal to 1 minus b squared on a squared. Then we can use the eccentricity to get our directrix and get our focus. So not too bad to do that first part. Then we want to do the second part, which is a little bit harder. So we've got, if that was an exam question, we'd have a nice bit to start off with, then a bit of manipulation. So what we're looking at here is that we want a condition for the line y equals mx plus c to be tangent to that ellipse. And that's what we need. We need, if that's going to be a tangent to that one, c squared must equal 9m squared plus 4. Well, let's manipulate that. So if it's going to be a tangent, then we'll solve them simultaneously. So that's why we've substituted y for mx plus c. So we start to expand it. We get rid of our fractions. So we can start to expand it out because we want to collect our x squareds. So we get the 36, we collect and get on the other side. We expand that bracket out. And then what we've done is got 4x squared and plus 9m squared x. So we collect that. 18mc x, so there's no other terms in x. And then our constants, 9c squared minus 36. Now, if this is going to be a tangent, we know that it should only get one solution for this quadratic equation because we're solving it simultaneously. And if it's a tangent, we should only get one solution. So if that's the case, we can get our discriminant, and our discriminant should be equal to 0. For discriminant's equal to 0 if we have one root. So we start to put that in. So we get our 18mc squared, 4 times a times c. So it should be equal to 0. So we put it equal to 0, and then start to expand out and be really, really careful with all these because there's m squared, c squared by itself, m squared, and so be really careful when you do the expansion. So we expanded that bracket with the 4 out the front. We put the 1, we multiply it out, and then start to collect our like terms. So we get 144c squared. So we take it up, the 324 m squared c squared cancels out. That's very nice. And then the 1296 m squared, 576 is left by itself. So we've taken that across because we know what we want to find. Now, hopefully, they're all divisible by 144, and they are. 144 goes in the 1296 9 times, and 576 4 times. But see the manipulation there. Okay, we've got to use the ideas that we have about the discriminant here, because if it's going to be a tangent there, it's only going to touch it at one spot. So the discriminant's equal to 0. So in question 3, we've got the point there in its parametric form, and it's a point on any point on the ellipse. M's the midpoint of SP. So we draw a diagram up. So P's there where it's tangent, and we've got our focus there, which is S, and so M's going to be the midpoint there. Now find the coordinates of M. So first thing we're going to do, we'll find the coordinates of M. It's not too bad. M would be AE plus A cos theta on 2 and 0 plus B sin theta on 2. So we just average them out, and there's our coordinates of M. Not too bad. We can leave it in that form. That's not a problem. The next part says find the Cartesian equation of the locus of M. Now, this is a little easy little manipulation we need to do. What we want to do is get back to a Cartesian equation. We're in a parametric form. What we've got here is the coordinates of M, and M can move around because P can move around. Because this can move around, the M would move around, and the M would move around according to this. So, but that's in a parametric form. Can we get it in a form that would be in a Cartesian? Well, we can if we look at our manipulation and do what we did in the extension 1 and get it back from parametric form into Cartesian form. So if that's the case, we've got x was equal to a outside of e plus cos theta on 2, and y is equal to b sin theta on 2. Now this is one where it's a little bit harder, so it just takes a little bit of a trick to go, well, let's get cos theta by itself. So multiply by 2, divide by a, and then we get a subtraction of e. So cos theta, when we get that by itself, gives us that form, and this one's just multiplying by 2 on b, and we get 2y on b, and we multiply by on both sides. So the trick here is, how do we eliminate theta and get x in terms of y? Well, the trick is here to square both sides. So square everything here, we get cos squared theta is equal to 2x on a minus c squared, and sine squared theta is 4y squared on b squared. Now we know from the 2-unit course that cos squared theta plus sine squared theta is equal to 1. There's our relationship. So we can get 2x on a minus c all squared plus the 4y squared on b squared would be equal to 1. So that's our manipulation that we can do. And now we've got x, a function now is in terms of x and y. Sorry, I shouldn't say function. our expression now is in terms of x and y, because it's technically not a function. So that's now how we need to do the locus in this case. A lot of times the locus isn't that hard as we go through, but that's a special manipulation. You're going to probably see more in the Extension 2 course than you would in Extension 1. You'll see locus and have to manipulate in Extension 1, but that's a special one. You need to get the square on both and use that relationship. We did do exercises like that in the Extension 1 earlier. And then the last part, prove that the locus is second ellipse with the center at the midpoint OS, where O is the origin. So that just takes a bit of a manipulation to go, well, we get back to this idea where we've got 2x squared, 2x minus EA on 2 all squared, and A squared. We get 4y squared on B squared. So we manipulate so we get the 4 lots of the E minus x minus AE on 2 all squared on A squared. Now technically that could go on the bottom and we get a number there, and the 4 we can go on the bottom there. It's just because that's all a number, and we're in that form where we've got an x minus h all squared on a number squared plus 4 plus y squared, or y minus k all squared on a number squared is equal to 1. So that general form of an ellipse, where we don't really have to worry too much about it, but in this problem we do. That's where it comes out. So the ellipse, therefore it's going to be an ellipse where the center would be EA on 2 and 0. So that would be the midpoint of OS, because S is E A, so half of that would be the point between the origin and the focus. So that's where we've proved that center is EA onto 0. So that was a little bit harder, but have a look at that manipulation. As I said, it'd be pretty rare because the syllabus doesn't really want us to get ellipses away from the origin. So it might happen in an exam that you'll see in the HSC, but it's not too hard. It's not really beyond you to have a look at that. So there we go. There's some exam type problems to look at and get ready for, and be ready to do some of that type of manipulation in class next week. So which we'll do a bit more work on that.